In this problem, we're asked to use Thevenin's theorem to determine V0 of t for t greater than 0. We're going to utilize two problem-solving strategies, one entitled S-domain circuits, and then the second one entitled applying Thevenin's theorem. So in our problem-solving strategy for S-domain circuits, step 1 says solve for the initial capacitor voltage and inductor current. And if we look at our circuit, note that the sources are multiplied by U of t, which says they don't have a non-zero value, or their value 0 for t less than 0. So in calculating those initial conditions, since the sources are 0 for t less than 0, all initial conditions are 0. So that completes step 1. Now step 2 says draw the S-domain circuit. Okay. So here's our S-domain circuit. And you can see we've converted everything over to impedances. The current source is 3 over S amps. The voltage source is 10 over S. And then when we're going to apply Thevenin's theorem, we're going to go in, and since V0 of S is across this element, we're going to remove this element from the circuit. We'll make terminals A and B. And then we're going to find the open circuit voltage and the Thevenin impedance looking back into those two terminals. Once we have that, then we'll hook the 2 ohm back up to find V0 of S. So then our task then is first remove the 2 ohm, find the open circuit voltage, then utilize that circuit, set the sources to 0, and find the Thevenin impedance. So let's calculate the open circuit voltage first. So we've removed our 2 ohm load, and here is our circuit to calculate the open circuit. And if we look at how we want to solve this to calculate the open circuit, first let's go in and let's assign mesh currents. I'll call that one I1, this one I2. So we know we have 2 mesh currents, so we're going to need 2 equations, but one of them is a constraint equation, and that's I1 of S is equal to 3 over S amps. Now we need another equation. Let's apply KVL to this mesh, and if we do that, we'll have 2S times I2 minus I1 plus 1 times I2 plus 2 over S times I2 is equal to minus 10 over S. So now let's take this and substitute in here, and when we do that and we rearrange some terms, we'll have 2S plus 1 plus 2 over S times I2 is equal to 6 minus 10 over S. If we multiply through by S, we'll have 2S squared plus S plus 2 is equal to 6S minus 10. So I2 is equal to 6S minus 10 over 2S squared plus S plus 2. So there's the mesh current I2. Now that's all we need to be able to solve for VOC, because we can now apply KVL to that loop to get an expression for VOC. So for instance, VOC will be 2S times I2 plus 10. So VOC 2 over S times I2 plus 10 over S. So we have 2 over S times 6S minus 10 over 2S squared plus S plus 2 plus 10 over S. And if we work on that and manipulate it algebraically, we'll come to this 20s squared plus 22s over s times 2s squared plus s plus 2. So that concludes the calculation of the open circuit. Now for Z Thevenin, we don't have any dependent sources, so we can go back to this circuit now and turn these two sources to 0. So if we turn that voltage source to 0, it becomes a short. We turn the current source to 0, it becomes open, and we find the impedance looking in to that circuit. So here's our circuit for calculating Z Thevenin. The current source was over here. Okay, we turned it to 0, and the voltage source was here. We turned it to 0. So if we look, for instance, these two elements are in series, and then they're in parallel with this. So for instance, Z Thevenin would be 2 over s times 1 plus 2s over 2 over s plus 1 plus 2s. So that gives us 4s plus 2 over 2s squared plus s plus 2. So that concludes the calculation of Z Thevenin. Now let's reconnect our 2 ohm load as shown in the diagram here. Here is Z Thevenin. Here's VOC. Now we can calculate V0 of S using voltage division. So we'll have 20s squared plus 22s over s times 2s squared plus s plus 2 times 2 over 2 plus 4s plus 2 times 2s squared plus s plus 2. So that's just voltage division. And if we work on that, then we can come up with V0 is 10 times s plus 1.1 over s squared plus 1.5s plus 1.5. So there's V0. Now, we need to now perform step 4, which is the inverse transform. So V0 of s is 10 times s plus 1.1 over s squared plus 1.5s plus 1.5. We need to find the roots of our denominator polynomial. If we do that, we'll have s is equal to minus 1.5 plus or minus the square root of 1.5 squared minus 4 times 1 times 1.5 over 2, and our roots are minus 0.75 plus or minus j.97. So V0 then can be written as 10 times s plus 1.1 over s plus 0.75 minus j.97 over s plus 0.75 plus j.97. And in our partial fraction expansion, we'll have k1 over s plus 0.75 minus j.97 plus k1 conjugate over s plus 0.75 plus j.97. Now, to find k1, we're going to multiply through by this factor and then let s equal minus 0.75 plus j.97. So k1 then is 10 times s plus 1.1 over s plus 0.75 plus j.97, evaluated at s equal minus 0.75 plus j.97, and that gives us 5.32, an angle of minus 19.84. And if we remember the inverse transform, we have complex conjugate roots. We have 2 times the magnitude of K1, so that's 10.64. E to the minus 0.75t, there's a 0.75. Cosine 0.97t, there's a 0.97, minus 19.84 degrees, U of t volts, and here's the minus 19.84.